So far, we've been solving trusses with something called method of joints, where we've been looking at every joint and applying our equilibrium equations to find the forces through every member. But we do have another method we can apply that is sometimes more useful in certain scenarios, and that is called method of section. And the ideal with this is that now we're going to take this truss and split it apart. So we're going to break it down into these separate sections by slicing through it and making it into these kind of two separate trusses so that we can analyze the forces through these members. If we cut directly through these members, we can look at the forces within each member. So the beginning of method of sections is the same as method of joints, where our first steps are going to be to draw the free body diagram for our truss so that we can solve for these reactions. And see what forces are acting on the truss as a whole. We apply our equilibrium equations, our sum of our moment, and some of our x and y forces to solve for those reactions. And then, this is where it differs from method of joints. Method of joints, we were looking at each individual point, looking at joint A, or looking at joint B, so on and so forth. Now we're going to be looking at this full section. So when I cut it off, the section that I get looks something like this. If I look at this BAG section, it's going to look something like this. Where here I have my cut line. And now what I'm seeing is I'm actually seeing the forces through those members. So the force in member BC, the force in member CG, in this case the force in member GF, along with those applied forces and any reactions that were there. So now I'm going to look at just this section of the truss and apply my three equilibrium equations. So my moment, my force in the y direction, and my force in the x direction. Here, now since I'm not looking at a single point, but I'm again looking at a system or a portion of the system, I'm going to have three equilibrium equations. My moment is included in this. So this is really useful if you want to know the force in one specific member that's kind of in the middle of your truss, right? If you were doing method of joints for this, you would need to start at joint D and then move to joint C, and do multiple joints if you wanted to do, say, member BC. This is in the middle of the truss there. You'd have to do multiple joints. But when we cut it with method of sections, I only need to do method of sections one time to solve for that BC. So it can be kind of a shortcut if there is a specific member that you're looking for or a specific force that you're wanting to find. Let's take a look at a couple of examples. So in this example, we're asked to find the forces in members BC, BG, and GE. So this makes for a really prime example of method of sections because we can see that if we draw a line through our truss here, we can draw a line that bisects through GE, GC, and BC. So method of sections makes the most sense rather than method of joints where you're starting at a joint and then you have to go from joint A to joint G, where you're doing this multiple times. So when we're looking at this, we've already got our little cross-section idea of where we're going to split it, but let's walk through each of the steps. One is usually to, identify your zero force members, see if that can save you any time. And in this case, we do have a zero force member. We have one zero force member here, and that is member GB, since GB is bisecting A to B and B to C. So we have one zero force member that's accounted for. Now we're going to go ahead and do our actual first step of drawing the free body diagram of full truss. So my full truss here, full body diagram, I have a 400 Newton applied force, as well as a 1200 Newton applied force. And then, of course, my reaction forces. One in the y direction at D, at the roller at D. And then an x and y reaction at A due to the pin at A. So this is it. It's really quite a simplification of our system, right? This is the free body diagram for the system as a whole. And what I can do with this is apply my equilibrium equations to solve for those reactions. So since I have two unknowns at A, I'm going to go ahead and take a moment about A and determine what dy is, right? So when I take my moment about A, it's going to be that 400 applied force is 3 meters away, and it is going clockwise, so it'll be negative. Then I have that 1200 Newton applied force that is 8 meters away, again, going clockwise, so it's negative. And then plus, since dy is going counterclockwise, dy times the 12 meters away that it is. So when I solve for dy, do the algebra, I get a positive 900. So I assume the correct direction, dy is pointing upward. Go through and apply my other two equilibrium equations. I can do my y summation, negative 1200, and then plus the dy value of 900, plus the ay value, gives me ay is 300 newtons. Again, assumed direction was correct because it's positive. So ay 300 pointing upwards. And finally, my x force summation. I only have the two x forces, 400 plus ax, which means I assumed incorrectly. If I do this, I get ax is negative 400. So ax is 400 newtons to the left. It is not to the right, as I assumed. So those are the first two steps. Again, this is the exact same way you would do it if you were doing method of joints. First two steps are always going to be the same, solve for the reaction. Now we'll get to the point where they differ, which is splitting it along this section line. So let's draw our free body diagram for that. When I split along this section line, I have AG, BC, AB, BC. Okay, so here's my split. Now I can choose to draw in member GB if I want to. It is a zero force member, so it's not going to matter if it's there or not. I'm just going to omit it because I think it's going to confuse me if I put it in there. So in my section here, I have the AY value I calculated of 300, the AX value calculated of 400, and then I have these internal force members that I'm looking for, which I'm going to draw pointing away from the truss to show that I'm assuming their intention. So I have GE at the split, and the force going through GC at the split, and then my force going through BC. So they're all along that section line where I've split the truss. So now that I have this free body diagram, I'm going to use this one to set up with my equilibrium equations for moment, y force, and x force to solve for these three members. Because again, this is what my question asked for, right? Just BC, BG, and GE, which are all here in my broken truss. I'm going to erase my reaction equations now that I have the only reactions that I really needed to solve this problem already written out here. So I'm going to do a moment first, and I'm going to take the moment about G this time, because that way GE and GC both pass through the line of action of G. Both of their lines of action pull through right? Point through point G. So if I take a moment about G equals 0 for equilibrium, all I'm going to have are my two applied forces, the 400 and 300 newtons, and then BC. So that makes it very easy to go ahead and solve for BC. So that would be BC times the 3 meters away. This height here is 3 meters as indicated in our original diagram. Then those applied forces. So negative 400 as it's going clockwise. Negative 400 times the distance of 3 meters away. Again, BC and 400 are both on this line down here. They're both 3 meters away. And then finally that 300 applied force, which again is negative, right, clockwise. And it is 4 meters away from G. This distance here. Here to G, this is G. Here to here is 4 meters, as indicated on our original diagram over here. 4 meters. So just doing the algebra on that, punch that into a calculator, it gives me that BC is 800 newtons, and it came out positive. So it is in tension. And I do want to mark with any time they're in tension or in compression, I always want to note that so that I know what direction it's going in. Right? Just as we use clockwise, counterclockwise for a moment, or we use direction arrows for Y forces and X forces, always want to mark it with a direction, and tension and compression act as the direction markers for these members of a truss. Alright, so that was one answer, is BC. I'll apply my other two equilibrium equations to get me the other two members that I want to know. So in the Y summation, all I have is the 300 Newton applied force, and then the Y component of GC. So this is a 3, 4, 5 triangle. Right? Our side is 3. This is 4, so this is 5. When I do this addition, I get 300 minus the Y component of this is going to be 3 minus 3/5 times GC. So GC is 500 newtons. Again, came out positive, so it is in tension. And then my last equilibrium equation, right? 3 unknowns, 3 equations, summation of my X forces. It's going to be that 400 Newton applied force, negative since it's going in the negative X direction, plus BC, which we already solved, that was 800, plus 800, plus the X component of GC, plus 4/5 now, 4/5 times 500, plus our last unknown, GE. Punch that in my calculator to do the algebra, and I get negative 800. Negative 800, which means GE is 800 newtons in compression. So that was it. All we needed to do was find those members. And I will say method of sections can be used if you're finding all of these members. You would just repeat the process again, taking a different section elsewhere on the truss, but it tends to take a little bit longer than method of joints. So I would say if you're solving for all members, you probably want to use method of joints. But if you're looking for a specific member, method of sections can be a good shortcut. Take a look at one last example where this is true. Now in this final example, I want to determine the force in member DC. So again, this is something where DC is this member of my truss in the middle of my truss here, right? I have a pin at A and a roller at F, and DC is kind of like off in the middle. So it would be kind of cumbersome with method of joints to go joint after joint after joint just to find DC when it's the only member I'm interested in. So it would work out a lot better to use method of sections and just cut through it and see if I can cut through DC and no more than 2 other members. Since I have 3 equilibrium equations, I can only have 3 unknowns. I want to make a cut through 3 members that include DC to solve for what DC is. So I'm going to go ahead and make my cut through here. I'm going to cut through DC, HC, and HI. Right? So my cut doesn't have to be perfectly down through the middle of something. It just needs to cut through 3 members. Only 3 members here. So I know where my cut's going to be. All I need now are the reaction forces that I'm going to be using. And I'm going to go ahead and do that by drawing my free body diagram, of course. If I draw just my basic outline of the truss shape, kind of this little awkward Pac-Man guy. I've got 40 kilonewtons, 50 kilonewtons, 30 kilonewtons, 40 kilonewtons, and then my support reactions. A pin at A, so I have AY and AX, and then just a roller at F, so I'm going to call this FY. So now I really only need the support reactions at whichever half of the truss I'm going to analyze. So for this, I'm only going to solve for FY because I'm going to cut my truss off right through here. So I don't need anything below this point, right? So what I'm going to do is take a moment about A, but then not even bother following through on solving my A reactions. I'm only going to go ahead and take the moment about A for this full free body diagram here. So I'm going to have my Fy is in the wrong direction. It is 4 meters from A. Then I have my next force, I have this 40. 40 is going counterclockwise, so it's positive, positive 40, and it is 2 meters from A. Right, this distance here, 2 meters. Then going on down the line, 50 does not count because it passes through the line of action of A here. Next I'll have this 30 applied force. It is going to be going counterclockwise, so it's positive, and it is 3 meters away. So plus 30 times 1.5. And then I also have this 40. That is 1.5 meters away, plus 40 times 1.5. And that's it. No A reactions because we're taking the moment about A. So I do the algebra, punch this into my calculator, and I find that Fy 46.25 kilonewtons, and it was positive, so the assumed correct direction was correct. So all I'm going to do is take this and create the free body diagram of my section. So my section here cuts off there at DC, goes across through G. I draw this in. H exists, this exists. So here's my cutoff. Right here is the cut line going right through there. I have the force through member HI, force in member HC, and then the force in member DC, along with those applied forces. We just solved this Fy is 46.25 and then those given applied forces of 40 and 50 on E and D. So since I want to just find member DC, this is really the only guy that I'm interested in. I don't care about HC, I don't care about HI. What I'm going to do is try to make it as simple for myself as possible. And in this case, since I have two unknowns that are at the H joint, I'm going to take a moment about H, because that eliminates those two HC and HI member forces. It eliminates the 50 that also passes through joint H. And so all I'm going to have is the Y component of DC, and then the 40 and the 46.25, all contributing to my moment. If I take a moment about H, I can really save myself a lot of time. Right, so if the moment about H is 0, I have the Fy applied force, 46.25. It is 4 meters away from H, right? This distance here is 4 meters. Negative as it's going clockwise. Then walking on down the line, I've got 40. It is going counterclockwise, so it's positive. And here it is 2 meters away from point H. And then the only other component that I have, I'm not going to have the 50, I'm not going to have HC, and I'm not going to have HI. I'm only going to have the Y component of DC. Right? Just this Y component of DC, because the X component is going to pass through the line of action of H. So here I'm only going to have the Y component. If I look at this triangle that it makes, I have a 1.5 and a 2 on the bottom. So my diagonal is going to be 2.5. So that is 1.5 over 2.5 is my ratio, times DC, and then times the distance away this is. This distance is 2 meters. So I do that algebra for DC, and I end up with a negative 87.5. Negative 87.5 means that it is in compression. So 87.5 kilonewtons in compression. And that's it. So we didn't even apply any of our force equilibrium equations. We were able to do this with just 2 moment equations, solving for the reaction of interest that gave us enough information to split the truss into a section so that we could find what member DC was. Saved a lot of time over method of joints, where we would have had to do multiple joints to find DC, so it can be a really handy shortcut if you know how to use it.